All right, so last time we looked at section 1.3, we got through the first part. We're going to finish up the second part right now. So we had talked a little bit about what domain and range was. Just as a quick reminder, when you are finding domain, there's two things that we have to be careful about. What's one thing that we are not allowed to do in math with arithmetic? Yeah?
Does it have like the equal to 0 or something?
Something with
Like
0.
canceling itself out or something like that.
It is something with 0. What can't we do with 0 in math?
Divide.
Yeah, so we can't divide by 0. So that's one issue we have to be careful about. So if I ask you for the domain of something like that, you'd have to tell me it's every number except 3, because you can't divide by 0. And there's one other thing we have to be careful with besides dividing by 0. And this, if you do it, will give you imaginary answers. And we want to avoid those right now as well. Yeah? Square roots. Square roots of what kind of number? Some square roots are okay. Yeah?
Negative numbers.
Negatives, right? So we have to be careful if the problem we're looking at has a square root in it. We do not want to take the square root of a negative number. So if you had something like this, you have to make sure that whatever you fill in for x causes what I just circled to be 0 or higher. Okay, it has to be 0 or higher. So in this case, as long as you give me a number that's 2 and higher, we'll be okay. If you give me a number smaller than 2, we're going to have a problem here. Okay, it's going to be a negative, and we don't want to do the square root of that. So those are the two things that we have to be careful about when we're finding domain. Okay, I think we mentioned those last time. So now, let's graph this and then find the domain and range. So it's f of x equals 16x minus x cubed. Okay. Are there any square roots in f of x? What do you think? River? No, no square roots. Julia, how about any fractions with a variable in the bottom? No? So the two things that could give you a problem in the domain are not in that, they're not in f of x. So, sorry. What do you think the domain is then? Yeah.
All real numbers.
It's all real numbers. Yeah. The two things that I said to be careful for are not in that question. So the domain is all reals. Range, that's usually a little harder. So for range, we graph it. So let's type this in on the calculator. 16x minus x cubed. Okay, let's start with zoom. What do we always use as our kind of starting window? Zoom 6. It's probably not going to be a great window. No, goes off the screen. We've got to look lower and higher because I want to see what's happening. Which two values do I need to adjust in my window? Y min, yep, and what's the other one?
Max.
Y max. How much lower and higher? Well, we don't know. I mean, this dips down somewhere. Let's try like negative 70, and let's do positive 70. That's going to give me a lot more space vertically to see the graph. I'm going to leave the x min and max where they are. Yeah, that looks good. That's fine. So we're going to learn a little bit more about these kinds of graphs later on. But the highest exponent in that equation is a 3. If you subtract 1 from that number, it tells you how many times the graph could turn. Okay? So this particular graph can only turn 2 times. Can I see 2 turns on the screen right there? Yeah, then it's not going to do anything else off the screen that you're not seeing. This part is just going to continue up and to the left, and that part's just going to go down and to the right forever. Okay. So again, if we didn't know that yet, that's fine, but that's a trick we can use. That, if you subtract 1, that tells you the number of times it could turn in a polynomial. It doesn't have to turn, but it could, and this one does. It turns twice. Okay, so looking at that graph, the range is how high and low it goes. What do you think the range is going to be in this one? Yeah? It's also all reals. Okay? Not only does it go left and right forever, it also goes up and down forever. So the easiest way to get the range is to graph it. They did ask for a complete graph. I didn't do that. So complete graph, you want to write these numbers down. Okay, so I use -10 to 10 for the x min and max, and -70 to 70 for the y min and max. Are those the only numbers you could use for a complete graph? No, there's other ones. I mean, -80 to 80 probably would have been fine. As long as you can see the shape, that's what you're looking for. Any question on finding the domain and the range? Okay. So now, let's take a look at this problem. So we've got a rectangular pool, and it has dimensions 30 feet by 50 feet. There's also a sidewalk all the way around the edge of the pool, and the sidewalk is the same width all the way around. We don't know the width like as a number, but they do tell us how to represent it as a letter. We're going to call the width of the sidewalk x. The area of the sidewalk is 600 square feet. So now, using that information that they give us, we're going to find the width of the sidewalk. That's the goal. So they've given us a lot of information here, kind of as sentences. What would make this problem a lot easier to think about? Yeah, Luke?
Make like a diagram of everything?
Yeah, let's just make a diagram of everything. So we'll just draw a pool with a sidewalk around it, and let's label the dimensions. Okay. So I'll scroll back up if you're still copying, but I just need space for my diagram. Okay, so we've got a pool, and we've got a sidewalk all the way around it. The pool is 30 by 50. This area, that's the pool. That's the water. And this is 30. That's 50. And the sidewalk is X units. That's all the way around on each side. Okay. Any question on the diagram? Now let's write down everything that we know. Okay, well, I already wrote 30 and 50. What else do they give me in this problem? Yeah?
The area of the sidewalk.
They give me the area of the sidewalk, which is how much?
600 square feet.
600 square feet. Okay. They also give me enough information to find something else. It's not given, but I can find it. What else could I find here? Pretty easily. I mean, the width of the sidewalk, we have to find that, but that's more work. This is easy to find. Yep.
Area of the pool.
Yeah, we could do the area of the pool, which is how much?
150 square feet.
How much?
150 square feet.
1,000.
Oh, wait.
Yeah, 1,500. Yeah. All right. Now we need to come up with an equation that's going to connect somehow the two things that we know and the thing that we don't know. which is the width of the sidewalk. So let's think a little bit about this big rectangle. Let me make it a different color. Make it purple. So looking at that purple rectangle, so pretend I handed you a piece of paper in the shape of that purple rectangle. And I said, I want you to hand back to me something that just represents the sidewalk. I don't want you to hand me anything else back. Just hand me back the sidewalk. What would you have to do to give me back just the sidewalk?
Cut out the pool.
You have to cut out the pool, all right? So if we wanted to have something that represents just the sidewalk, you'd have to take the big rectangle and take away or cut out the pool. So what option or what operation in math do you think means to like cut the pool out? Yeah, we're going to subtract out the pool. We're going to subtract the pool from the bigger purple rectangle. So we've got to find the area of the big rectangle, and we're going to cut away the pool from it. And that's going to leave us with just the sidewalk. Any questions on that kind of idea? The area of the sidewalk is the big rectangle minus the pool. Now we just have to start to fill in what we know. What's the area of the sidewalk?
600 square feet.
600. And what's the area of the pool?
1,500.
1,500. Now I need the area of the big rectangle. And this is where the letters are going to start to come in. Well, it's a rectangle. What's the formula for area of a rectangle? Yeah. Length times width. Length, width. Okay. So the first thing I need is the length of the purple rectangle. Well, it's bigger than the swimming pool. I know the part from here to here is 50. How much is this piece on the edge on the bottom? How long is that part? Yep. Sure. Anyone? We won't have a number for it, but we do have a way to represent it. Yeah, it's X. That's the sidewalk part. And how about this piece over here? That's also X. So the length of the entire bottom is that, plus that, plus that. Which, when we combine that together, is how much? 2x plus 50. Yep. So that's the length of the bottom. And then we can do the width the same way. If you break the width into those three pieces, what's the width of the big rectangle? Yep.
2x plus 30.
2x plus 30. And now we need to solve that for x. That's our equation. Here's the area of the sidewalk, the area of the big rectangle, and we're going to take away the area of the pool. Okay, so with the parentheses, we have to distribute. 2x times 2x is going to give me how much?
4x squared.
4x squared. What about 2x times 30?
60x.
Yep, and I'm going to put that off to the side because I'm going to combine it with what's 50 times 2x?
100x.
100x. So that gives me 160x. And last calculation for the distributive here is 50 times 30, which is?
50.
Yep.
1,500.
Yep, plus 1,500. But what's going to happen there?
Cancel.
Yeah, the 1,500 cancels out. And you're left with an equation that has a highest exponent of 2. Okay, so it's not cubic. That'd be an exponent of 3. It's not linear. That would be an exponent of 1. What do you call an equation that has a highest exponent of 2? Begins with a Q. Yeah?
Exponential.
Begins with a Q. Yeah?
Quadratic.
It's a quadratic. Yeah. So that's a quadratic. When you are solving a quadratic, what do we want to get it equal to? A certain number we always want to get a quadratic equal to, especially if we're going to try to factor it. Factoring, algebra 1, 0. You have to get it equal to 0. Okay, we're not, you do have to know how to factor. We're not factoring this one because it's not factorable. Factoring comes up later on with other stuff, but not for this one. So how would we get that equal to 0? Yeah?
Subtract 600 on both sides.
Okay, subtract 600 on both sides. And then what could you do with that? Even before, if it was factorable, we would do this even before. Yeah?
Divide by 4.
Yeah, I divide everything by 4 just to make the numbers a little smaller. No, it's not factor. Okay, so you don't get a nice answer. What's another way you can solve an equation that has a highest exponent of 2 besides factoring? Yeah?
The quadratic formula.
Yep, quadratic formula. So that was the real point of this problem, just to review, not teach a whole lesson on, but just kind of quickly review quadratic formula. Can somebody tell me what the quadratic formula is? Yeah?
Is it negative b plus or minus the square root of b squared minus 4ac divided by 2a?
Perfect. We just have to make sure we understand what the a, the b, and the c are looking at our problem. First of all, they're all numbers. Can anybody tell me what a is going to be there? What?
X squared.
They're all numbers. So the a, the b, and the c are not variables.
Would it be 40?
B is 40.
Okay.
Force? I'm sorry, Luke.
1.
A is 1, yes. And what about C? Yeah, Nico?
Negative 150.
Negative 150. Okay, so A is what's in front of it. A, B, and C are all numbers. That's A, B, C. Okay, now we just fill them in and get our answer. So we've got negative 40 plus or minus the square root of 40 squared is how much? 1600. Minus 4AC. All divided by 2a, and what's 2 times a in this case? Just 2. Now, if you look under the root, we're going to be subtracting a negative number. What happens when you subtract a negative?
It adds.
Yeah, it's going to turn into addition. So if we want to deal with that right now, we can make those positive. What's 4 times 1 times 150?
600.
Yep, 600. I'm just going to put that right up here temporarily. And now let's write our final answer. Well, final answer before we change it to a decimal. 1600 plus 600 gives me how much?
2200.
Yep, 2200. Okay. So now we got to see what that comes out to when we type it in. How many answers is this giving me? Yep,
2.
2. Now, we're talking about the width of a sidewalk, so it can't be 2 different answers. It has to only be 1. So most likely one of these answers won't make sense. Let's try negative 40 plus the square root of 2200 plus square root 2200 divided by 2. That makes sense. The sidewalk could be almost 3.5 feet wide. Sure. So about 3.45. Let's do the negative. Let's do negative 40 minus square root 2200. Okay, so negative 43.45. What do we think about that answer? No, why not?
Because distance can't be negative.
Distance can't be negative. So mathematically, does that solve this quadratic equation? Sure. Does it make sense in the context of the word problem? No. So the answer is 3.45 feet. Okay. So any question on that one? It's probably the hardest word problem we do today. But it is, the diagram, I think, helps a lot. Yeah. Okay, so second to last thing in this section is projectile motion. Projectile motion might be something you study if you take physics. We're not really going to get into what it is and all the physics behind it. We have a formula that allows us to represent projectile motion. That's all you need to know. We can use this formula. And what this formula basically tells us is how high an object is going to travel. That's what it tells us. So this part of the formula is the height. They tell you that right up above. Now the height that an object is going to reach depends on a couple things. What do you think the T stands for?
Time.
That's time. It's in seconds. So when I throw something up and then catch it, how high it goes depends on what time you look at it. Are you looking at it a tenth of a second later? 1 second later? How much later? The other thing two things that are going to affect how high the object goes is what was the speed I threw it at? Was it thrown gentle, or was it thrown a little bit harder where it goes higher? And then was it off the ground when I threw it? Did I put my hand on the ground when I released it? Or was the pen already up in the air 4 or 5 feet when it left my hand? Okay, so the initial height of the object also makes a difference. That could be if you were standing on a building and you threw an object. Things like that. So that's our formula for projectile motion. Okay. And here's the problem they give us. A rocket is being shot straight up from ground level with a speed of 64 feet per second. Doesn't matter what they're going to ask me. I should take the information and fill it into the equation up above. So what are the 2 things that they gave me in this problem?
Initial height and velocity.
Yeah, they gave me this and that. So those are the 2 things they gave me. So let's fill in what we can. So the height equals, and what comes right after the equal sign? This part never changes.
-16t squared.
-16t squared. That -16 has to do with gravity. Okay? And it has to do with the fact that we're using feet and seconds. So if you did something like this in physics, you might use the metric system. That negative 16 would be a different number. Okay? We're using negative 16 t squared plus, what was the initial velocity?
60.
How far? How much?
64.
64. So we're going to fill in 64t. And what was the initial height of the object? Yeah?
Would it just be 0?
0. And the reason it's 0 is because they're telling you the rocket was on the ground when it started. And the height is measured off the ground. So if the initial height is 0, you don't need to put plus 0. Okay, so there's an equation. Don't know how we're going to use it yet, but at least it represents the word problem. At what time will the rocket be 50 feet above the ground? So they're giving me one more piece of information. 50 feet. Now we have to fill that into our formula as well. Where's the 50 feet going to go? Yeah. S of t. Yeah. S of t is the height. And in this case, 50 feet is height. So you're going to plug in 50 right there. So you've got 50 equals negative 16t squared plus 64t. Now, I asked you this before, very similar kind of equation. Highest exponent there is a 2. That makes this a quadratic. So I could go through and solve it just like I did last time. I could put the 50 over on the other side, identify my A, my B, and my C, and fill it all in and do quadratic formula. But I already did quadratic formula. So let's do this one on the calculator. Okay, to do it on the calculator, just take this equation, take the 50, put that in y1. Take the negative 16 t squared plus 64, you got to use x as your variable, and put that in y2. So you should have something that looks just like that.
Why can't you use t as your variable?
Because the calculator it only views x as a variable when you're in function mode. It would view t as a constant. Yeah, it would view it as a constant. Because it's a memory position in the calculator to save a number. Yeah.
Where's the negative sign?
Right below the 3. Yep. Okay, I don't remember how our window was set up, but I do know when we're talking about time and height, they both have to be what kind of number? Yeah?
Positive.
Positive. So negative time doesn't make sense. Neither does negative height. Okay, we're not launching an object into the ground. If it was going underground, then it could make sense, but we're not doing that. Okay, so let's set our window up like that. Let's hit graph. So there's my 50-foot mark, and there's the height of the rocket. Now, this is a quadratic equation, and it has 2 answers, just like the sidewalk problem did. But this time, both answers make sense. Why do both answers make sense this time? Nico?
Because they're both positive.
Yeah, they're both positive. But why does the rocket hit 50 feet twice?
Because it's 50 feet on its way up and on its way back down.
Yeah, on the way up and on the way down. So we're going to write both answers. We can call it time 1 and time 2. Okay, did we talk about finding an intersect on the calculator last week? We did? Where is the intersect feature? How do I get to that? Nico?
Hit second and hit trace.
Second trace, yep.
And then you go down to intersect.
We go down to intersect. Now, since there are 2 of them, we need to put the cursor closer to the one we want when we do the guess. For the first part, pick a point anywhere on the blue. That's fine. You can pick a point anywhere you want on the red. That's fine. Time 2 is at 2.94 seconds. And now we have to repeat that to do time 1. So second, calc, intersect. And move our cursor anywhere on the blue, that's fine. Anywhere on the red. And now put your guess closer, doesn't have to be right on it, just closer to the left one. And on the way up, the rocket hits 50 feet at about 1.06 seconds. We could have gotten those exact numbers using quadratic formula as well. Just would have taken an extra minute or so. Okay. Any question on how we got those intersects? Okay.
Would you want both answers if this was a test?
Yes. Yes, absolutely. Yep. Because in the context of this word problem, both answers make sense. In the sidewalk problem, they did not. Both make sense. So what is the maximum height and when does it reach it? All right. Well, first of all, which graph are we looking at to find the max height? Red or the blue?
The red.
Yeah, we're looking at the red. So we don't even need to look at the blue one. If you want to get rid of the blue one, you can. You can leave it. Point is, you don't need it anymore. We're done with it. And I don't think we've done this yet, but if you press second, trace, there's an option here that will help you find the maximum height. Anybody have a guess which option that is? Yeah? It's option 4, maximum. Like intersect, it will ask you 3 questions. Right now, my cursor is way off the screen. It's at -80. You need to be able to see your cursor to do this. So if you press the right arrow, now it's at -100. I'm going the wrong way. You press the left arrow till you start to see it come up, and there it is. The first question it asks is left bound. I need to take my cursor and position it somewhere to the left of the maximum. Once I get it to the left of the maximum, I press enter. Next question it says is right bound. You have to take your cursor and put it somewhere to the right of the maximum. So now you've got this kind of column it's going to look at to find the maximum. The guess doesn't really matter. You can put the guess close if you want to put it somewhat close. But just hit enter. And that's what we got. Now, I did this in the other class before, and they got 2.00000001. I got 1.9999998. Anybody get the 2.0 number? It's basically the same thing. I'm going to round it. So first question, what is the maximum height? Luke?
64.
Yep, max height is 64 feet. And this happens at how many seconds? 2. Yeah, it's 2 seconds. But the calculator can't really do, this calculator can't do algebra. So it's just guessing really fast. And it got 1.9999998, which is basically 2. So 2 seconds. So any question on how we got the max height and the time that it occurred? Okay, so that's a new, I think that's a new thing, finding a maximum. So that's something you can add to your list of things you know how to do on the calculate menu now. And the last thing in this part. We're going to graph what's called a piecewise function. And what a piecewise function is, it's two functions on the screen at the same time. That's all it is. And the two functions together make one picture. Now, you might say, well, yeah, we've done that. There's two functions on the screen at the same time, like that. Yeah, but that's two different graphs. We're going to graph one picture using two formulas. Okay, so that's a little different. That's two formulas creating two pictures. We're going to do two formulas creating one picture. And the way that a piecewise function works is, let's say I decide to split my domain at the number 0. And I tell you, okay, if you pick a number less than 0, I want you to plug it into the first one. And I would tell you what that formula is. If you pick a number more than 0, you're going to plug it into the second formula. And I would tell you what that formula is. So depending on if you pick a number more than 0 or less than 0, you have a choice of which formula to plug it into. And they will always tell you the rule for which one to plug it into. So here's our example. They're not splitting the domain at 0, they're splitting it at 1. Okay? So think of a number in your head, any number you want. If the number you're thinking of is less than 1, I want you to plug it into the top one to get the answer for y. If you were thinking of a number in your head that was 1 or higher, I want you to plug it in to the bottom one to get the answer for y. So now you just have a choice of what formula to use depending on if your number is less than 1 or more than 1. And I'm just going to show you how you graph that on the calculator. Okay, so that's really the whole point of this. It's purely a technology thing. Okay, let's graph 3 minus x squared. And for now, just watch me. Don't type it in yet on yours because I'm going to have you clear it in a second. If you graph 3 minus x squared, it looks like that. But what the calculator is doing is it's graphing it for every x value. I want this graph to all of a sudden get to 1 and then stop. I don't want to see it do anything else down here. I want it to just stop when it hits 1. And this is how you do it. You're going to have to put in parentheses 3 minus x squared. Now, if you just put parentheses, it's going to do exactly the same thing. Okay, still looks the same. Everyone agree it looks the same? Okay. What I have to put next to that is this, when x is less than 1. So open a parenthesis, put the x, and now I need to show you where the less than symbol is, because I don't think I've shown you that yet. It's under second math. That's where you can find all your inequality symbols, and I want the fifth one. Okay, let's graph that now and see what it does. So it comes up, and then it just stopped. This part shouldn't be here, but I can't do anything about that. Okay, that's we'll draw over that with black so we don't see it. But there's our parabola, and then all of a sudden it just stopped at 1. Now I'm going to have a new graph start at 1, and that's the bottom one. So we're going to type in that one, in parentheses again, x cubed minus 4x. And if that's all you put, it's going to graph the bottom one everywhere. But I only want to graph it 1 and higher. So x, and where's my inequality symbols again? Second, math. This time I want option 4. Yep. All right, let me zoom out a little so we can see the whole thing. So there's the blue one. Just stops, ignore that part. Same thing, ignore that part. And there's the red one. So it's two different graphs, or two different equations making one picture. And let me just put in the axis right here. So pretend like you can't see the colors. That's what this picture looks like. Now, there's one thing we need to do the calculator can't. This was the blue one. This was the red one. When we get to the end of the blue one, do we include or do we not include the very end of the blue graph at 1? We don't include it. What kind of circle do you put when you do not include something? Yeah?
Is it
Open. That tells me do not include the endpoint of the blue one. Now for the red one, it starts at 1. Do I include or not include the 1 on the red one? Yeah?
included?
I include it. So that should be a closed circle. So that is what your graph should look like. And that's called a piecewise function. And this is how you type it all in. Just like that. Okay. Any question on typing in a piecewise function? All right, so that was what was left in 1.3. So now we'll review a little bit of 1.4, which is on y equals mx plus b. I don't think there's anything in 1.4 you haven't seen yet. I was going to ask you what do you call that. That's the slope-intercept formula line. Does anybody remember what the m stands for? Julia?
Slope.
Slope. And how about the b? Yeah.
Y-intercept.
Y-intercept. Yep. Slope and y-intercept. So anything that can be written in that format is called a linear function, even if it doesn't look like it's in that format. If you had something like, and you may say, oh, that's not y equals mx plus b. Yeah, but I could fix it so it is. I could bring the 2x to the other side. Now it's y equals mx plus b. Okay, so anything that can be rearranged to look like that is a linear function. And it's linear because it looks like a straight line when you draw it. No complex numbers here. Okay, M and B have to be real numbers. So fractions, decimals, negatives, those are all fine. But nothing with like an I in it. That's imaginary. Yeah. Yeah. Okay, so we said that the m is slope. What's the formula to find slope? Anybody remember? Yeah.
Rise over 1. Run.
Yep, rise over run. Or what? If you think about it with like x's and y's, there's a calculation you can do. Yeah.
y2 minus y1 is at the top, and x2 minus x1.
Yep. So again, rise over run, that works if you want to remember it that way. Or y2 minus y1 over x2 minus x1. Yep. So that's the formula to find the slope. Now, there are two lines that are special cases. If you have a horizontal line, does anybody remember what the slope of that is? Is
0.
0. And how about a vertical line? Yeah?
Undefined.
Undefined. Perfect. So those are two special cases. The other thing that is special about them is they are not y equals mx plus b. With a horizontal line, it's just something equals a number. Does anybody remember what letter is on the left when you draw a horizontal line?
X.
Nope, not X. Yep.
Y.
Y. Think about when we graphed y equals 50 for the rocket problem. It was exactly horizontal at 50. So it's not y equals mx plus b. How about vertical? Yep.
X.
That's x. And you can't draw a vertical line on the graphing calculator, because there's no way to type in x equals. It's all y equals. And there's no way to change those. Okay, so those are two special cases. All right, so let's see if we can find the equation of the horizontal and the vertical line that passes through the point 2, 3. So here's your point. What would be the equation of the horizontal line that goes right through the point 2, 3? Yeah, yeah.
Would be y equals 3.
Yep. So special case, y equals 3. And what about the vertical line? That goes right through that point. Yep.
X equals 2.
X equals 2. Okay, so again, those are special cases. Any questions on that? Okay, again, it should be all stuff you just kind of trying to recall from Algebra 1. Slope-intercept form. Well, here's something that's not y equals mx plus b, but we could fix it. What would be your first step to get y by itself in that equation?
Subtract 2.
Subtract
2x.
2x. Okay, is that y equals mx plus b now? Jack?
You have to divide by 3.
Yeah, we still have to divide by 3.
Could you have divided by 3 before you moved it over?
Yes. Yep. And now you get y equals negative 2/3 x plus 2. What's the advantage of having it written in this format compared to the format it started in? I mean, technically it's the same thing, but there is a reason why we might want to get it in slope-intercept form. Would slope-intercept form make it easy to do? Yeah?
It's easy to find the slope and y-intercept.
Okay, it makes the slope and y-intercept jump out because they're right in the format, negative 2/3 and 2. And what else does that format make it easy to do?
Graph.
Graph it. Yep. So if you have to graph the line, slope-intercept form is a really easy way to do it. Okay, so that's the advantage of it. Now, slope-intercept form isn't the only form. There is another format, and it's called point-slope. What letter is missing from point-slope that we had in slope-intercept? Something's missing. Yeah.
B.
Yeah, B. So the advantage of point-slope is if you don't know the intercept, you don't need it. So it's y minus y1 equals m times x minus x1. You fill in for this, for that, and for that. Those are the three things you have to plug in for. The x1 and the y1 are a coordinate you're given, and the m is the slope. So find the equation of a line that has a slope of 1/2 and passes through the point negative 2, 3. Let's first make sure we know where all three of those numbers are going to go. They're going to go in those three boxes. But it matters which one you put where. what is the 1/2?
Slope.
Which is m. That's my m. What about the -2? Where's that going to get plugged in, Jack?
X1.
That's my x1. And the 3? That's my y1. Yeah. So just fill those in. Be careful if you have minus a minus. That's going to change something. So we've got y minus y1 equals m times x, and then what's going to happen inside those parentheses?
The 2 becomes a positive.
Right, it's x minus x1, but that's x minus minus 2, so plus 2. So that is your answer in point slope. Now, if they said to you, rewrite that in slope intercept, what would be your first step on the right-hand side? Yep.
Distribute.
Yep, and what are you distributing?
Well, 1.5 to the x and the 2.
Yep. So the first step would be to distribute. Now it's in neither format. It's kind of halfway between the two. And my last step to get y by itself would be
At 3 equals side.
add 3. Directions in this problem did not say you had to get it in y equals mx plus b. I'm just showing you how you would do it if it did say it. Okay, so top one is point slope. Bottom one, slope intercept. Okay. Any question on that? Okay, parallel and perpendicular lines. What does it mean if two lines are parallel? They never touch. And what about in terms of like slopes and intercepts? And that, could somebody explain it using those words too? But that's visually what it's going to look like. Yeah.
They're the same slope.
Same slope.
Different
what-
intercept.
Right. Has to have a different y-intercept. Because what if they were same slope, same intercept?
It's the same line.
Yeah, then it's just the same line right on top of it. But that doesn't count as parallel. Okay, so those are parallel. And perpendicular. Does anybody remember if two lines are perpendicular, their slopes have a connection? They're not same slope though. They're it's actually two words. Yep.
Oh, never mind. What if it's 2 words? I was going to say negatives.
Well, they are opposites. That's half of it. But they have to be more than opposites. Really?
The reciprocal?
And reciprocals. So like if you had one line with a slope of 2/3, perpendicular to that would be -3/2. Those are opposites and they're flipped. So let's pick one of those. I think I picked a parallel one. Write an equation of a line that's parallel to this and passes through the point 1, -2. Well, if you want to be parallel to this equation, what do you have to know about that equation? Yeah, you got to know the slope. If you don't know the slope, how are you going to be parallel to it? So let's find the slope by rewriting that in y equals mx plus b. So I'll minus the 3x. And then I would have to do what to get my y by itself? Yeah,
Divide by -2.
divide by -2. Okay, I don't really need to finish, I just need the slope. What's the slope of the line that they gave me? 3/2. Yep. So the slope is 3/2. What's the x value of the point that they gave me? Gabby?
Sorry, what was it?
What's the x value of the point that they gave me?
1.
1, and the y value?
2.
Negative 2. So now all you have to do is plug in those three numbers, just like we did in this problem right here. Just plug all three in. Any question how you plug those in from here? Now, if they, instead of parallel, what if they said perpendicular? What would change out of those three things? The m, the x1, or the y1? Only one of them would need to change. Yep, the m would be different. What would the m be if that said perpendicular?
Negative 2/3.
Negative 2/3, yep. So you do the whole problem just using negative 2/3 for m. Perfect. Okay. Any question on that? Okay. And then that's it. Okay, so the last thing we're going to look at is graphing a line and then shading it. Okay. So a linear inequality is when you see an inequality symbol instead of an equal sign. So instead of y equals mx plus b, let's say y is less than mx plus b, or y is greater than. Now when you graph a linear inequality, you need to do two things. When you draw your line, it's either going to be solid or dotted, and then you have to either shade above it or below it. This chart explains all of that. Whenever your inequality symbol has the equal to under it, you use solid line. When it doesn't have the equal to, dashed line or dotted line. If the inequality symbol is a less than or equal to, you shade under it. If it's a greater than or equal to, you shade above it. Now, there's only one time, it's kind of a special case, where you don't have an above and a below. What kind of line could you draw that doesn't have a section above it and a section below it?
Vertical.
Vertical. When you have a vertical line, there's no above and below. So where do you think you would shade for a less than symbol if it was vertical? It's not below the line. It would be to the left of it, the way that it's pointing. And if you have to shade above, well, above means to the right. But other than that, every other line you draw has an above and it has a below. All right, so I think I can keep that up and look at our last question. Okay, so the first thing we need to do is draw our boundary line. What format did we say we usually like a line in if we want to draw it? What's the format that makes it easy to draw a line? Caleb?
Slope intercept.
Yeah, slope intercept. And can you tell me my first step, Caleb, to getting that in slope intercept?
Yeah, subtract the 2x from both sides, or like move it to the right side.
Okay. And do you want it before the 4 or after the 4?
Or before the 4.
Yeah, if we're trying to get to mx plus b, we want it before. So what would you have right here?
I'd have negative 2x is less. Oh, wait. Just plus 4.
Plus 4. Okay, so almost there. What's my last step?
Get the y line.
Yeah,
Divide by 3.
divide by 3. And there you go. So that's what we need to graph. When you're graphing a line, do you use the slope first or the y-intercept? Yep,
Y-intercept.
y-intercept. So the y-intercept here is 4/3 is like 1 1/3. So it's like 1.3 repeating. How would I mark my y-intercept on that graph? Where do I have to go? Yep.
Like a little bit above the 1.
Yeah, go a little bit above 1. So let's say maybe about there. So there's my y-intercept. And from the y-intercept, the slope tells me how to get to another point. How would you interpret that? -2/3 is like a directions to the next point. Yeah.
It'd be down to left 3. Or would it be to the right?
Well, if you're at a point and you go down and to the left, you're going to get a positively sloped line. So what do you think?
Down 2 to the right.
Down 2 and to the right
3.
3. Yep, perfect. So we're going to go down 2, 1, 2, and then right 3. Yeah, again, it doesn't land on a grid mark, so it's not a terribly nice graph. But let's go down 2, right 3. Do this as many times as you need to. It's good enough. And now we're going to draw our line. Should it be solid or dotted? Caleb?
Dotted.
Yep, this is going to be dotted. So a little bit off, but that's not too bad. Okay, so that's dotted. And the last thing I need to do is either shade above or below. Where am I going to shade for this one? Yeah,
Below.
below. Okay, and it doesn't have to be perfect. You're just going to shade everything that's underneath there. And that's it. Any questions on that? All right, so that's 1.3, the second part, and then 1.4. Okay, you've got about 15 minutes left. Okay, so the first part of the homework is on page 31. And then the second part with the y equals mx plus b and graphing inequalities, all that, that's page 42. So we'll go over that first thing tomorrow, and then we will take a look at 1.5